This is Lecture 9, a lecture on random variables. Random variables is a difficult concept, so my advice is to read the section on random variables in the book, to go over the PowerPoint slides multiple times, and possibly even listen to the video and watch the video a couple of times in order to get the terminology that we're going to use throughout the semester dealing with random variables. So let's first talk about the idea of a random variable. So if you're trying to measure something, let's say temperature or measure voltage, or you're trying to count the number of arrivals or departures in some time interval. So let's just think about the number of arrivals. Let's say you're in a hospital and you want to count how many arrive in a 5-minute time period. How many patients arrive in a 5-minute time period? So the arrival is some kind of random event. How many people are going to arrive, you don't know ahead of time. It could be that there could be one person arrives in a 5-minute time event, no people could arrive, or you could have some kind of bus accident and 10 people could arrive. So the number of arrivals or departures is kind of random, but we're counting those and we're actually taking this a random event and then assigning to it some kind of numerical value, a real number. That's what a random variable is. It's a mapping function. It's a function which assigns outcomes of a random experiment to real numbers. So you have some type of sample space here. So remember when we talked about tossing a coin, your sample space was heads or tails. If you're rolling a die, your sample space is 1, 2, 3, 4, 5, or 6. If you're counting the number of people that arrive in a 5-minute time interval, you could go from 0 all the way up to, it depends on the capacity of the hospital, right? So you have some kind of sample space, and to that sample space, what you're doing with a random variable is you're assigning some kind of number. So tossing a coin is a random thing. Rolling a dice is a random thing. You're going to assign some kind of real number to this random event, to these numbers in the sample space. Formal definition, again, x, the random variable x, is a mapping. It goes from our sample space to the set of real numbers. X might be undefined or infinite for a subset of S that has 0 probability. And moreover, what the mapping has is that for any real number A on the number line, if you look at the inverse mapping, so negative infinity all the way up to A, the inverse mapping is what are the events, the sample points in S that give me a real number that is less than A. So this is our subset of script A. Remember, this is in our probability model. Script A is the collection of all subsets of S. So here, this is the events in S, or the sample points in S, so that that real number is less than or equal to A. We may not cover the entire real line, so if we're thinking about the number of heads in a two coin toss, then the number of heads can be 0, 1, or 2. So the range can be a lot less than the real number line. And the range is denoted by A, which is the space of X, or called the state space of X. In the example that I just gave with the two coins and the number of heads in a 2-coin toss, then X is called a discrete random variable because the range of X is finite or countably infinite. If, however, we're measuring how long a thunder boom lasts, the length of time that it lasts, then this could be 23 seconds. It could be 1 minute and 5 seconds. So the interval now that could range the amount of time that this thunder boom lasts could range across this whole interval. It's not just discrete numbers. And so in that case, X is considered a continuous random variable when you're thinking about the range being some interval. Okay, so our terminology. It's really difficult to think about the terminology because lots of times we think about that real number as being the random variable. The real number that on that real line is our random variable, our mapping, at some sample point of S, at some event. Or we can think about little x as being some generic value on that real number line. Our mapping, which goes from our sample space to our number, is actually called the random variable. So it's easy to get capital X and little x confused a lot of times, because lots of times when we're thinking about, so if you think about the project that you did for the first assignment, we had realizations, right? So think about little x as a realization. What value could, for instance, our SIR model take on? What value could our model take on at this time step, right? So there's a whole collection of different values that it could take on, and one of those numbers for one of those realizations was our little x. Now our entire mapping is capital X. So let's give a more concrete example. Let's consider 3 coin tosses. So we're going to toss a coin 3 times in a row. Whether or not it lands on heads or tails is variable, right? It's a random event. So we're going to let x be the random variable that represents the number of heads that you can possibly get in a 3 coin toss. Depending upon the outcome of the 3 coin toss, capital X can take on different values. So you're going to go from this sample space. So what is our sample space here? Our sample space, we're talking about 3 coin tosses. We could get tails, tails, tails. We could get tails, tails, heads. We could get tails, heads, tails. We can get a variety of different combinations of tails and heads in those 3 coin tosses. Remember, that's our sample space. Now, X is the number of heads in those 3 coin tosses. So what values can it take on? Well, if we toss a tails, tails, tails each time, then the number of heads is just 0. So here, this number 0 is our number on our real number line. Here, x of s equals 1. We only have 1 heads. There are 3 different ways that we could get 1 head. So if our event is either one of these 3 things, then our value of our mapping, our range, is 1. Here you can get 2 different ways you can get 2 heads, and there's only one way in which you can get 3 heads. So capital X, our random variable, is the mapping that goes from this sample space that consists of all of these together to the numbers on the real number line. And then our little x could be a number such as 2. Little x could be 0, 1, 2, or 3. But capital X is this mapping. Shorthand notation, which is what we're going to use quite a bit, capital X equals little x basically means the event. So the event that you get a little x when you look at the mapping of that event. So for example, if we have capital X equals 0, it means the event TTT in our previous example. So capital X equals 0 means the event that there are no heads, which is the event tails, tails, tails. So capital X less than or equal to X means the event, or the events, so that our realization on our number line is less than or equal to some number. So going back, if we have capital X less than or equal to 1, then what are our events? These 4 things are our events. These are the events that can happen so that our capital X is less than or equal to 1. Because here it's a 1 or a 0. we can talk about the probability of an event. So what's the probability that capital X equals 0, for instance? So this is the shorthand way of writing it. This is the long way of writing it. And what is the probability of our capital X being less than or equal to our little x? So for instance, what's the probability that capital X equals 0? So let's go back to the previous slide. What is the probability that we're going to get 0? Well, there's 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes that are equally likely, right? So what's the probability that we're going to get 0? It's just going to be 1. What is the probability that we're going to have capital X less than or equal to 1? Well, there are 4 possible ways of doing this. So we have 4 out of 8. The probability capital X is less than or equal to 1 is 1/2. Okay, so next time we're going to talk more about the probability notation. So now you want to go to lecture 9B to get more of the specifics about probability and some of the terminology. And then we'll be talking more about random variables then.